Hi everyone, welcome back to our conference, and today we are going to have a talk with Michael Di Prisco. He's senior backend developer at Jointly, educated in the development field and still trying to get his head around it. Full stack developer with a strong experience in backend development and passion about all things in jazz. So, couple talk about him. He usually wears Guardians of the Galaxy socks, as they have proven to be luckily talisman for Michael. And welcome Michael and his talk, navigating the event loop for blazing fast applications. Enjoy.
Hi, Christina. Thank you for introducing me. So, hi everyone, and welcome to my talk. As we said, leveraging the event loop for blazing fast applications. So, I'm Michael Di Prisco. You can find me online as Cadiman. I'm from Italy, and I'm currently a senior backend developer in Jointly. This is the only good photo I will ever use in my lifetime, so thanks to my wedding photographer for it. I'm also a LogRocket Content Advisory Board member, and I like to call myself a waster of NPM storage because I'm an open source contributor, mainly in the JavaScript field, so NPM, and I'm a serial pull requester. I'm not the topic of this talk, so I suggest we go ahead and start our journey as we have a lot to cover. So let's start with a really bad joke, but someone had to make it in a JavaScript conference. So I promise you will learn something, and I'm sacrificing my credibility for just this joke. So at least we will try to learn something today. So let's start with our table of contents. What are we going to talk about today? So first thing first, what is the event loop? So we will briefly talk about the event loop in JavaScript. Our second topic will be the Microtask Queue. So specifically, we will go in a deep dive into the Microtask Queue. And the third thing will be a live demo. So we will provide what we learned before and put it inside a simple application. So I don't have both the expertise and the time to extensively talk about the event loop and to properly connect all the dots about how it works. So please excuse me for taking shortcuts and abstracting many concepts. Today we will concentrate on how the event loop works at a high level and concentrate mainly on the usage of the Microtask Queue to provide performance improvements in our web applications. If you really want to know more about the event loop and how it works in different runtimes, more about runtimes in a couple of minutes, please search for the awesome presentation by Jake Archibald, In the Loop, or the incredible Create Your Own JavaScript Runtime by Eric Wendell. So let's start with a couple premises. So one step back before starting our journey. The first question we have to answer is JavaScript single-threaded? Yes and no, but yes. So there's been a lot of debate during the years about JavaScript being single or multi-threaded and how this language works. Yet the answer still is yes, JavaScript is a single-threaded. Web workers and service workers in the browsers or child processes and forks in Node and Dino are APIs provided by those runtimes. But in the ECMAScript specification, let's say the list of rules governing the language doesn't allow for multi-threading. And yet it can allow you to execute non-blocking operations even in scenarios where multi-threading will be the only answer. So let's go with our second question. As we are going to talk about a specific runtime, let's go through what a runtime essentially is. So being a non-compiled language, JavaScript runs in some sort of container and a program that reads and runs your code. The container must do two things mainly. The first is parse, convert, and execute your code. And the second is provide some objects, prototypes, functions, and APIs for your code to interact with. So the first part, the part involved in parsing, converting, and executing your code is called the engine. The latter, so the one providing you the APIs and some additional functionalities, is the runtime. So let's take the most famous duo of runtimes in the JavaScript world. So browsers, implementations, and Node. Both of them, let's talk about the Chrome browser mainly, so we can simplify a lot of things. So both the Chrome browser and the Node runtime share the same engine, the V8, yet their runtimes differ a lot. Node.js provide you structures such as streams, buffers, libraries like fs or path, APIs such as the file system ones, and the require method, for example. while the browser provides you DOM objects, the window objects, web APIs, etc. So there are different APIs and different functionalities brought in. Let's take the console.log as an example. So you all know what it is, and we all use it in production. So don't lie to me, because I do it all the time. So what if I told you V8, so as we said, the engine responsible for both the Chrome implementation and the Node.js environment, doesn't know what console.log is? Yeah, that's right, because this is the part of the web API in the case of a browser runtime like the Chrome one, and a different implementation in the Node.js source code. As per Node.js, you can look at a nice implementation of the console in the official library, so in the official Node.js source code, so on github.com/Node.js at lib internal console constructor.js. So every runtime implements its own flavor of the event loop, usually leveraging some key concepts we will discuss in a second. One step back, even if I'm mainly a Node developer, this talk will be based on the browser runtime and its implementation of the event loop, because it will be easier to provide a demo and it will be easier to follow. The browser implementation mainly differs from the Node one because of how some queues in the event loop interact with the loop itself. So in Node, we could say, oversimplifying it, that we have one event loop per process, while in the browser we have one per agent. For agent, we mean a Chrome tab. So if you have a tab which has a blocked event loop, you can still close that tab and proceed with your navigation in other tabs. So blocking the main thread of a tab doesn't block the other tabs from doing their job. So that said, how many runtimes are there? We talked about the Chrome one and Node, but there are many others. As I like to say, at least one more than when I started talking. But the most common ones are mainly Node.js, Dino, from the same creator, Ban, Workerd from Cloudflare, and browser's own implementations. So let's now go to our main question. Now that we know what is a runtime, and that JavaScript is single-threaded, now let's try to understand how the event loop allows us to provide a non-blocking input-output, so non-blocking main thread, while still leveraging some functionalities that should be only part of a multi-threaded language. I want to give credit to Lydia Halley for creating this really empowering GIF explaining how the Microtask Queue and the Macrotask Queue work and their order of execution. So, as you can see, we have the call stack and a Microtask Queue, which is emptied every time a task is being executed, and a macro task following it later. So the Microtask Queue is usually filled with, it's effectively filled with things like process.nextTick, promise callbacks, async functions, and the queue microtask, which will be our main topic in a second. As per the Macrotask Queue, we have mainly the set timeout, set interval, and set immediate. So you can ask, what's the difference between the Microtask Queue and the Macrotask Queue? Is it just the order in which tasks are executed? Not at all, and we will talk about it mainly later. So let's consider what is the event loop and what are the main parts composing it. As I like to say, the event loop is rather a concept than an actual thing. As we said, it's implemented in different ways in different browsers. But the event loop is mainly a concept. Implementations in different runtimes can vary, yet the main parts are usually consistent. So we have mainly the heap or the memory heap, which is some area in memory used to store objects. And to provide some context, the garbage collector attacks, let's say, this heap when it needs to free up memory. Then we have the stack or the call stack, which is the ordered list of operations to be executed. So being single-threaded and non-concurrent, JavaScript can grant predictable execution steps, and we will talk about it in a second, just following the first in, first out model in the call stack. Queues. As we said, we have two queues mainly in the implementations we are looking at, the micro and the macro, and our list of callbacks waiting for their time to be executed. So let's simplify it in this way. So queues vary between runtimes, but are usually, as we saw before, filled with timeouts, asynchronous calls, event listeners. So whatever is not immediate and doesn't have to be executed at this exact moment. So it doesn't have to be put exactly in the call stack or the stack as we want to call it. So let's talk about the three main concepts of the event loop. three things really worth mentioning because they will be really important for the live demo later. So the first thing is run to completion operations. So run to completion means that every portion of our code, an execution block, a function, etc., is executed till its end before another element of the call stack is executed. Okay. So you may ask, what about concurrency? So I continuously hear about JavaScript being concurrent, being parallel, being single, multi-threaded, etc. Well, a lot have been said about this topic in JavaScript, but please be aware that JavaScript has no way of executing concurrent code. This is important. The main thread, of course. It can do something similar thanks to the worker implementations. So as we said before, spawn processes and use different threads, yet the main thread executing the main block of your code and responsible for keeping it in line with your application and keeping your script alive isn't concurrent in any way. So do not, please, misunderstand asynchronicity with concurrency, because they are two totally different concepts. And this is the real difference between JavaScript and many other languages. So leveraging this event loop implementation allows it to be single-threaded, but non-blocking. Yet it cannot be concurrent. B, leveraging queues to free up the thread. So leveraging queues, as said before, means putting in some queue every non-immediately executable operation in a specific area and wait for it to be ready before executing it. The two most important queues, as we saw, are the Macrotask Queue and the Microtask Queue. So let's go to the third thing worth mentioning. So the timeout isn't granted. So what do we mean by the timeout isn't granted? Let's say we call a set timeout of half a second in our application and then wait for it to be executed. So for our callback to be put back in the stack. This set timeout just grants us that the execution of the callback will be at least 500 milliseconds, so half a second in the future. Yet it could even last 10 seconds, for example, if our main thread is blocked. So please remember, when using these timeouts, how the event loop works and how a blocking thread works. So if you need time correctness, please use timestamps checks instead of timeout calls. What's the difference? A timeout call is, as we said, a set timeout. A timestamp check is some part of your application in the life cycle of your application, which checks some expiration timestamp, for example, before executing a callback. Okay. So as we just said, the main concept of the event loop is to allow you to have a non-blocked main thread. So why don't we try to block it? So I decided to use a llama because I love llamas in this example. We have this GIF that will be start moving, and then we have two buttons. The first one is the IO blocking button, and the second one is the non-IO blocking button. The difference, of course, is blocking the main thread or not. So as we see, we can continuously click on the non-IO blocking function and it keeps working. But as soon as we start pressing the IO blocking button, everything stops, everything breaks and nothing works. So let's do it again because the GIF is really fast. So as you see, I'm continuously clicking on the non-IO blocking button. And then as soon as I click on the IO blocking one, everything is frozen. So what happened and why is that? Let's look at our blocking code being executed. As you can see, clicking the button calls an unsafe loop function, which is simply an infinite loop. What does this mean? It means that the call stack keeps growing with tasks to do. In this case, of course, just an empty execution between curly braces, yet is still an operation to be put in the stack. So this is effectively an infinite loop, even if it isn't doing anything, because it has to evaluate the condition inside the while parentheses and then execute the empty but still existing code inside the curly braces. So let's now look at our non-blocking loop. As you can see, we are just calling a set timeout of 0 milliseconds, but still doing the same infinite loop again, calling the safe loop function in this case. So why doesn't it block my UI? Well, simply because a set timeout is a task scheduled later in the future, as we said before. So it can be put in what the event loop calls the Macrotask Queue. So a specific queue which will wait for the next time our sphere will do a complete turn. So let's imagine this event loop like a circle with a sphere continuously ticking 360 degrees. So wait till the stack is empty and then bring in the first runnable task. So we never block the event loop because we are effectively continuously moving to the next step, the next tick of the event loop, our safe loop execution. So it is effectively a loop that will never end, but still it is not blocking our main thread. So it is a non-IO blocking operation. Fun fact, when talking about the Macrotask queue in the event loop, we usually talk about a set, so a different data structure from a queue. Why is that? Because as we just said, the event loop grabs the first runnable task in a set instead of dequeuing the first task in a list. So it's a little different. It's really a simple difference, but it's worth mentioning. And this is the Macrotask queue. But what about the Microtask queue? So what is the Microtask queue? After all this talking about the event loop and its queues, or as we learn, its sets, let's talk about the Microtask queue, which is, well, a queue and not a set, unlike what we said before about the usual tasks being implemented, the usual queues being implemented in an event loop. This is because the Microtask queue can only be filled with runnable tasks provided by us. So the developers interacting with the event loop. So they are runnable by definition right when we put them into the queue. So no need to take the first runnable one, as they all are effectively in the Microtask queue. So the Microtask queue acts in a specific part of the event loop and is probably one of the most misunderstood parts of the whole event loop thing, because this queue effectively acts as soon as the call stack is empty. So in the context of a browser, it usually happens right before the event loop tick is completed, and it is almost starting to re-render. I say usually because there are certain specific cases when this queue loses some priority, but this is not the topic of this talk. So let's say in an unusual context, though, it actually leverages the moment between the call stack empties and the rendering time, effectively acting as a last step before starting the page rendering phase. So after all this talking, what are we building today? So I promised you a live demo. This will be our third part. We have 4 steps to victory. So the first is a project scaffolding. What do we mean by a project scaffolding? A simple HTML page with nothing particular inside it, with a simple title and a couple of things inside it. A basic signal implementation. So let's take a minute talking about what I personally mean as a signal. So what are we going to build today, and a couple of things we will discover. So we will leverage JS classes or ECMAScript classes, as we want to say it, even if they are just mainly syntactic sugar, because they are simpler, of course. So everyone not aware of the prototype pattern can still follow this implementation without asking without having questions. And a signal is in this case mainly one-way data binding from JavaScript to the HTML. So we will just provide a class in which the objects can attach to a node, a DOM element, and after attaching to that DOM element can leverage some JavaScript functionalities to change effectively the HTML markup. So the third step will be a barebone benchmark. So a simple benchmark where we will track the time needed for 100,000 updates, 1 million updates. We will have a look. We will probably go for 1 million just to have some wow effect in the end. And it's a secret. No, I'm just kidding. The whole talk is about what we'll do here. So we will implement the Microtask queue, and we will try to understand how much of a difference it can make. So making our application effectively blazing fast. So if you want to see some code, follow me. So we have a simple VS Code implementation now. So nothing hard here. We will create an index.html file, simple enough. And we will go with the help of Emmet for a simple HTML5 page. My signal implementation. We will have GitHub repository later, so please don't worry if you can't follow exactly code line by line, because there will be a different implementation provided later. So let's start by creating a simple paragraph. So let's put an id on it, and let's call it main paragraph. And let's, with the help of Emmet, of course, let's do some lorem ipsum. Okay, now let's create a script tag. I know it's not the best way to do this, but please, I want to keep it simple. So let's go by creating our class, which will be called signal. Okay. And now let's start by putting a couple of things. So an initial element, so a DOM element attached to it, and a value. So I know we can leverage private properties and private methods for classes, but I wanted to keep it simple. So you will not look at something like this. We will just simply prepend an underscore for our, let's say, private properties. So let's go for the constructor. And we will, of course, have an element and a value being passed to our constructor, and we will put it inside. Okay, this.l equal L and this.value equal value. Okay, so here we are. Now our simple signal is doing mainly nothing, but we can start instructing it and creating it. So signal equals to new signal. I don't trust Copilot enough, so I will write it by myself, and we have plenty of time, so let's try to use it. Main paragraph. Okay, here we are, and then we will pass a value. Let's say hello world. Of course, yeah, we don't need this because we are going to effectively control in a one-way data binding way the content of our main paragraph. So let's remove it. Then we will need a rendering function, of course, because we need to bring in the inner HTML of this element. Of course, I'm keeping it simple. As I said before, later I will provide some slides, a slide with a QR code you can follow to look at a different implementation, but we will talk about it later. So please try to keep it simple with me, okay? So our rendering function just brings the inner HTML following the value being passed, okay, the internal value. So let's call this.render in our constructor. Now that we have all this scaffolding ready, let's go live. I will move the Chrome browser below. Okay. I hope you can see it. I will zoom it in a lot. Okay, here we are. So we have a simple implementation now. We have our hello world being printed on the console. Of course, I cannot, I can leverage this console to change my text. So let's say ABC, and then we can call the render function. But of course, we want to make it faster. So we will provide some magic inside this implementation. So let's start by providing an API to the users using, to the other developers using our signal. So let's provide a magic getter for our values, which will return this dot underscore value, and then a magic setter with a val being passed. So this dot value equal val and this dot render. Okay, so what changed now? Let's take a minute to talk about it. So our effect will be this one. So I can change the value. Let's say what we are missing here. This dot value equal val. Okay, this dot render. Okay, seems good. Signal dot value equal ABC. Okay, you can see that our value is changing and our DOM is being updated. So our node element, so our DOM node is attached, and we can control it with our signal. We are using some JavaScript magic, some object-oriented programming magic. Of course, as I said, a prototype implementation would be better. We will talk about it later, but we have the scaffolding needed for our application. So now let's move to our third step. So we have the scaffolding, we have our basic signal implementation, and now we can move to the part where we do some benchmarking. So let's try to, okay, const start equal new date dot get time. Of course, we can just do this. In a Node.js environment, we could use a better and more accurate API, which is the performance one. But as always, we are keeping it simple. So let's go with the const start equal date dot get time. Then we will just try to go for 100,000 updates. And of course, we are just moving our signal value. We are just changing it, calculating our end time, and then let's say time taken and minus start milliseconds. Okay, so let's save it. Date.getTime is not a function. Yeah, sure, because it's not, yeah, we don't need date.getTime, but we need date.now. That's what we need. So let's do it for also for the end, that date.now. And here we go. Okay, time taken 135 milliseconds. Okay, so now let's try to clutter this up a little. Okay, so maybe create our, let's say, paragraph 1, paragraph 2, and paragraph 3. So let's go with our signal 1, paragraph 1, 2, and 3. So we are just trying to bring in some latency, some work for our main thread to do, okay, so that we can better leverage the Microtask queue later. So let's say we are moving to this approach. Okay, hello world 1, hello world 2, and hello world 3. Okay, let's go. Time taken 394. Circa 400 milliseconds. So let's improve this number. So let's say we are doing 1 million operations 3 times, so 3 million operations. So as you can see, my input is my main thread is blocked. So if I try to update it again, I cannot copy and paste anything inside the page until it's done. So now that it is done, you can see the cursor changing. I will do it again. So as you can see, everything is blocked on my side, and then I can. Okay, so we have 4 seconds effectively where our event loop is just doing its job and blocking our main thread. So we need to fix this, of course, because we cannot wait 4 seconds for it to render everything. Okay, so let's put something here. So let's go back to our signal implementation, and let's move our implementation from a immediately render mechanism to a queue mechanism. So is it queued? So this will be a flag, of course. This dot queued equal false. And as soon as we now try to move the new value, okay, we will effectively keep updating our internal value because, for example, and you will see this later, we can have some event listeners, for examples, that have to be triggered when the value changes, yet our rendering phase shouldn't be bored with 3 million operations every time, okay? So if this is not queued, this dot queued equals true, and then window dot queue microtask, and we can call a function inside here. So this dot queued equal false, this dot render. So before looking at the result of this operation, of course, we have to remove this dot render from here. Let's talk about what we did here. So as we said, let's zoom in a little. Okay. So we have added a queued property, putting it to false, of course, in our constructor. Rendering, of course, this didn't change because the render phase is always the same. So we have an inner HTML and this.value. So that's it. But we changed our setter. So of course, we just say, have we already queued this operation for our next rendering phase? If so, don't do nothing. We could just do it in a different way. So if this dot queued, continue. But we don't care, okay? So if this is not queued, let's put it into our queue. So let's bring this flag on true, and then leverage the window queue microtask. So this is exactly the API we need, and this is the only thing we are looking for. So a simple function being executed when our queue microtask will bring our item in. So this will be effectively our callback. So we put it again into a non-queued state, and then we will render. So are we ready to look at the difference? As we said before, let's go back to our implementation so we can have a look at how this worked before. Okay, let's render this one. 3.7 seconds. Let's do it again. So this is mainly the average, 3 and x. 3.8. So now let's go to our implementation, and if I didn't do anything wrong, 61 milliseconds. So we brought 50x improvement in our simple application. Of course, you could ask, why should I do 3 million operations inside a single rendering? But that's not the question you should do. You should ask yourself, in a simple life cycle of my applications, how many times do I need to re-render something on my screen? So how many times will effectively this render function being called? If you look at a simple active application, so with some animations, with some interactions with our user, of course, you can see there are dozens of updates being done. Of course, having a 50x improvement in performances is really awesome when these dozens of updates becomes hundreds, thousands, and maybe millions, because if your application is really high in animations and interactions, you can easily reach 1 million interactions, okay? So 1 million updates using this Signal implementation. So this is something, and of course, remember that everything that allows you to improve performances without any disadvantage should be done. Okay, so this is a rule we all should try to follow. So we saw some code, and now we can say, wow. So if what I said earlier was well explained, and this result is what many of you might have expected. If not, please, as I said, go to the look at the Archibald and Eric Wender's job. So our last question is, so why don't we always use the Microtask Queue? So as we said, this is a 50x improvement in performances. This is awesome. It's easy to implement, and we can do it right away in every application. Okay. So why aren't we effectively doing this? Well, all that glitters is not gold. So despite the enormous improvements in performances we can have by leveraging the Microtask Queue, it doesn't mean it's always the best solution. As we said earlier, this queue effectively acts before the event loop starts a new tick. Okay, so effectively acting as a last step. So if you bring in too many tasks, we will still find ourselves blocking the main thread. What I mean by that, so let's try to look at our safe loop implementation and try to change the behavior by not doing a set timeout, but a promise.resolve. Promise.resolve means resolve it immediately, so put it inside the Microtask queue. And then call the safe loop function. I need a glass of water, so please excuse me. Okay, here we are. So promise.resolve effectively puts it into the Microtask queue, and then it executes it immediately. So as soon as our call stack is empty, we call the Microtask queue. So we say, the event loop asks the Microtask queue, do you have anything to bring into my stack? Yeah, of course, I have the safe loop function. The safe loop function is executed, puts another execution of the safe loop function, the callback, inside the Microtask queue, and then empties itself. Now the event loop asks the same question. Okay, so I'm done. Can I do a next tick, or is there something inside the Microtask queue? Yeah, there is this safe loop. So we continuously clutter our main thread just by doing one single operation. So we will effectively create an infinite loop. Okay, so as we started with a bad joke, I thought it would be nice to end with an even worse one. So let's say the event loop is the only infinite loop you will ever want in your app. So please be aware of one thing. We will go back a little because we need to do this. Remember, even if in this GIF, this really awesome GIF, the Microtask queue acts effectively right before the Macrotask queue, this is not exactly the correct order of execution, because one is inside the current tick of the event loop, and the other one, the Macrotask queue, is effectively one of the first things being done after the tick of the event loop. So effectively, using set interval, set timeout, and set immediate, we are not creating a block in our main thread. And of course, I can agree with you that process.nextTick and setImmediate are the worst names for these kind of functions, because effectively the process.nextTick acts in the current tick of the event loop, and the setImmediate isn't immediate but acts in the next tick of the event loop. Yet this is the specification, so we have to stick with it. So let's go. We have to repeat our animations all over. So I hope it's all clear, and why you should leverage the Macrotask queue and the Microtask queue. And if you have some questions, of course, please provide them. But first, if you want to see a complete implementation of a Signal leveraging the Microtask queue, please find it following this QR code or search super simple Signal on my GitHub profile. Remember, I am Kadiman, so Cadienvan, and you can find the super simple signal implementation, which doesn't leverage the class implementation, but a different one, a prototype-based one. So ready for your questions.
I
No
have lots of
problem.
questions, and thank you for your talk. It was really interesting for me to know because I consider event loop to be the base of knowledge.js. I have lots of questions, and I will start with the light one. How often do you turn on the recorder while coding? Because I
I'm
know you
sorry,
have lots
I
of.
lost you for a couple of seconds. Try to repeat,
How
please.
often do you? Yeah, sorry. How often do you turn on the recorder while coding?
I still can't hear that specific word. How often do you?
Turn on vinyl recorder while you're coding. I know
The
that you
recorder.
have
Oh,
lots of vinyl. Ah, okay. You don't
oh
hear.
yeah, the vinyl record. Yeah, of course. I have it right behind me. So I usually bring in some Elvis Presley music. So just to relax myself when I code.
Okay. How often do you implement Microtask in your job?
Well, I always like to think as performances as a first-class citizen in my applications. So whenever I can leverage the correct queue, I usually try to do it. As I said during the presentation, I'm mainly a Node.js developer. So my main implementations, my main usage of the event loop is on the backend side. Yet the concepts still remain the same. So whenever I have some let's say high workload, so for example some heavy operation that has to be done, I usually leverage one of the two queues we talked about, so the micro task or the macro task, depending on, of course, the immediate need I have for that operation.
Do you consider that knowledge of event loop is one of the steps for improving performance?
Yeah, sure. The event loop is fundamental for improving performances because it provides so many simple yet powerful ways. As we saw now, we had a 50x improvement in our performances just by leveraging, just by moving our rendering function to a simple callback. So of course, the event loop is one of the main things you should study when you are talking about performances, or in general when you are using some sort of JavaScript runtime.
You mentioned Ban and Dino. Dino is hard to implement now because Node doesn't work correct at the moment. But what about Ban? What is your opinion about it?
Okay, so it's hard to have a really profound and deep dive opinion about Ban or Dino, because the runtimes are always changing and always upgrading and updating themselves. Ban is pretty new, honestly. Yet I think Dino did some really great choices, but Ryan did. I think Ryan, the creator, did a so great job with Node that effectively the market share for Dino couldn't increase so much. So that's the only thing I think is missing from Dino. So we have TypeScript, we have a really big and performant runtime, and so I think this is really the only thing wrong with Dino. Now they implemented the Node API layer, so you can effectively use the package JSON and Node modules inside the Dino. So this is a really great advantage. And for Ban, I think it's a really awesome player. But as far as I can tell, working with Ban isn't easy. So working effectively with the maintainers of the project isn't easy because they chose to implement some mechanisms to make Ban work as fast as it does. But of course, the developer experience isn't good. So I see ban as a nice experiment. So as I said earlier, you can look at an Eric Wendell video, which is publicly available on YouTube, about creating your own JavaScript runtime. And he talks about effectively the difference between, if I'm not wrong, Zig, which is the language behind ban, and Node-like implementation, which leverages C.
Can you tell about cases when you used event loop in your workflow and it helped you?
Okay, so as I said, I will talk about a node-specific example because it's something that comes to my mind right now. I had a situation in which I had many calls to an endpoint, so an HTTP endpoint, an API mainly, and it had to do some work before providing an output. It was some math calculation, some heavy math calculation. So what I did was move into the Macrotask Queue, so the next tick of the event loop, some of that work, so that of course, I increased the timeout of every person calling my API of some milliseconds, but didn't clutter my main thread with all the work it had to do. So I moved in different steps of my application lifecycle the execution of that math calculation.
I think it's going to be my last question. Is it more important to know about event loop in front-end part or back-end part?
It depends on the scale you are working on. Okay, so I can say for 90% of the developers, we are working on small to medium-sized projects or small to medium-sized parts of big projects. So mainly the browser is the main part I will try to consider for using these simple tricks of the event loop. But of course, if we are talking about big portions of big projects, also the backend must have its part. So of course, we are talking about a Node D, no ban, or Worker D backend, of course. But we should try to leverage, if not the event loop APIs, at least the event loop concepts every time. So always consider the fact that if something too heavy goes into your main thread, everything else will have to wait. Okay, so even if I suggested to look at it from a browser perspective, because it's fairly easier to implement some great optimizations. We can see it both for the event loop and, for example, the CSS tricks that you can use to improve performances. So you can have a bigger impact, of course. Yet for example, in a Node environment, you will have different challenges, and the fact is it's not easy. It's not always easy to understand which part of your Node application is slow. So Node is even harder to debug, to understand where the event loop isn't doing its job efficiently. We can, of course, use some tools like the Doctor.js or Clinic.js, look at some inspector, so some garbage collector information, but it's harder for a Node.js application to leverage the event loop and to understand where the event loop is not doing its job. So yeah, I'd suggest going to the browser.
Okay, thank you so much, Michael. We are out of time, and let's switch to the Voice Discord channel. Thank you so much for your talk. See
Thank
you.
you a
Bye.
lot.